All right. Hey, GM everyone. We're here today to talk about Circom. And I'm just doing just a brief presentation on what Circom is, how it works, and we'll go through a demo circuit together. So let's start by just answering the question, what is Circom? But for that, we need to understand like a basic knowledge of just zero knowledge proofs. And they're basically a protocol that allows you to prove that you know a mathematical fact without telling people what you actually know. And it's this is achieved through cryptography, and I'll show you how we do it later on. For the purpose of this, let's first just start by defining Circom as a domain-specific language that allows you to define arithmetic circuits that can be used to generate ZKPs. I'd put out two previous tutorials, basically blog posts that kind of delve into ZK without delving too much into the math, and I introduced the concept of arithmetization, which basically is more suited for ZK generation as opposed to working inside of Turing complete languages. And so this is a further continuation in that series. But let's begin. What are we going to be covering? We're going to be covering some basic Circom features, pragma, templates, and various other things. I'll show you how we use the Circom library. And finally, I'll show you how we use Snark JS for proof generation. And essentially, whenever we're thinking about zero knowledge proofs, they're basically divided into two primary components, which is one is like your constraint generation, and then the next is like the proof generation. And so the constraint generation is comprises of us defining the actual circuit using a language, and then defining the constraints thereof. And once we are done with that, we could then go into the proof generation, and that's where Snark JS comes in, because we use and Snark JS uses the Grot16 protocol or Plonk and Flonk as well. So let's start by diving straight into the code, right? Let's begin. I'm going to go through this at a high level. If you don't know how to install Circom, I'll refer a link to the documentation that will show you how to install Circom. But Circom is basically a Rust application that uses a Rust compiler on the back end for you to be able to actually get started. For this particular demonstration, I'm using a rock, paper, scissors example that essentially allows three primary inputs, right? Rock that we're going to express in the form of numbers, and so a rock would be 2, paper was 3, and a scissors is 5. And essentially, as you would remember, rock scissors beats paper, paper beats rock, and so on and so forth. But yeah, rock doesn't beat scissors. Yeah, similar rules that we would all be accustomed to. But let's look at it like from a code standpoint, right? And how we start. So when you're looking at a Rust application, the first thing you have to define is a pragma, which is at the very top here, that tells the Rust compiler what version of Circom to use. There's been very many versions that have come out since I first initially worked on this script, and there's more where that's concerned. And then from there, you could come. We are pulling in a comparator circuit from the Circom library, right? And what does that mean? Let's actually go through it together. So let's do a yarn install here. So if I go into my example folder here, see into Circom or dash example. As you can see, I just have 2 files in there. And for now, I just want to focus on one simple thing, which is starting this yarn application. So I'll do a yarn edit, go through the process. Yes, it's version 1, Circom example. So in the new folder, I just have a file that ends with .circom. And the other one is just a text file that I use for everything else. Yeah, MIT, yes. No. And that's it. So we have a package JSON defined. So let's add the Circom lib to the project. And when we do that, we essentially pull in the Circom library. And now we have a node modules folder here that has the library kind of defined there. And if we we keep going through it, we'll see the circuit here. And here's a comparator template. And it has a number of different templates, well, file, but it has a number of different templates defined. One, it checks if is 0. The other one is false equal if enabled, so on and so forth. The other one checks if it's equal. And this kind of highlights a key feature of Circom, which is its modularity. And so you could keep defining circuits on top of circuits. And this is how we have even more complex circuits, such as the ECDSA signature that's been defined. I'm just going to remove this because this was something else I was trying to do here. But yeah, so let's go into the code. We are defining our rock, paper, scissors example. We have an input here that is the player 1 input. And then we have the input here that's defined as a player 2 input. And we have a output here that is the winner. And this is what we pass out of the circuit back into like Solidity or whatever else that's consuming this particular circuit. And these are the parameters. So if it gets a 0, it's a draw. If it's a 1, then player 1 wins. If it's a 2, it's player 2 who wins. And we're going to go through this particular piece, which is, I guess, the most important piece here, where we're looking at how we add constraints. And if you're looking at how we do this, where this would have been, if we were writing this in any other programming language, it would be if we're checking player 1's input here is equal to 2, or player 1 input, or this is equal to 3 or 4, something of that sort, right? Where we have an OR gate here, then do XYZ, right? This is how you'd express this in a traditional circuit. I mean, in a traditional programming language, or like your Turing complete programming language, but in zero knowledge, and specifically in Snarks, we have to express everything in algebraic statements, and we have to break them down into statements that, like on a basic level, compile to things like x equals y plus z, or 0, or y equals p times v, or something of that sort. And so with simple multiplications and verifications. Why? Because this allows us to generate constraints, and it's the constraints that we generate that essentially convert this into a algebraic expression that we could then confirm on the other side. And so what we're doing here is essentially converting, we are declaring what is known as an intermediate signal, and persons with a electrical background would understand like what the intermediate signal, but it essentially allows us to hold values temporarily. When we do that, we're essentially calculating and saying if the player 1's input is either 2 or 3, then the check could exist inside of that value. And if you work out this particular calculation, it essentially always evaluates to 0 if the input is 2, 3, and 5. And so this kind of demonstrates like the most significant change in terms of a paradigm that a programmer should have when they're looking at how to work with Circom and how to essentially express themselves in quadratic constraints, essentially. And the rest of the code, I won't go through the full code. What I will show, other than that, is how we're using the component here, which is the is0 component, and we're basically pulling in the value here of is0 into we are instantiating the is0 component here. So we have a keyword called component, and we are defining a value that goes into the component, and if it is 0, it is then held in this particular area here, This is the intermediate value that will hold whether or not the value is 0. And this is the signal that we're actually defining there. And once it exists here, we basically read back out, and it'll give us the assessment of whether or not it's 0. And if you go further down, you'll be able to see where we actually consume this later on, right? And so you could do this in this particular way, or we could have everything defined in terms of just simple quadratic constraints that you continue to define as you move along. So that's essentially it. That's the biggest paradigm from a code standpoint that one has to make when working with Snarks in particular, which is a check that would have been a simple if statement would have to be provided, would have to be expressed in the form of a simple quadratic constraint. And in so doing, we then enable the verification to actually happen mathematically. And that is the biggest piece. Beyond this, we could deploy the code. There are a number of different commands that we could run, and I'll take you through them now. That will essentially enable us to deploy this together. So first of all, for you to actually deploy this, you need to define it here. And the first step is we're defining the circuit, and we're basically compiling it. And we're compiling it, and you'll see a number of different files have been added to the project. And it tells us here the number of public inputs that we'll have. Private inputs are 2, which is what the players provide, and instances, and so on and so forth. And importantly here, we have files generated here in terms of, you could have this C++, where you have a different workflow. But today I'll be showing you how to do this using Snark JS and the JavaScript route. And we have the constraints that were defined as well, and these are what enable and facilitate the generation of the constraints that we're going to be using inside of the rank 1 constraint system. So from there, we jump into the generated folder, and the anatomy of this is that we have the keyword Circom, we have RPS defined. We say we want a rank 1 constraint system. We want to also generate a WASM file, and it also generates the symbols for us and does the output in JSON. So you'll see all of those corresponding files are created here. You have the symbols, rank 1 constraint system file, which is for the compiler, and so on and so forth. So let's jump into the JS folder. So cd into the RPA-JS. And you see here we have 3 files that were created. Generate witness. The other file you need to create for yourself is the input file. So let's first create like an input JSON in here, and create a new file here. Call it the input.json. And let me just copy this off of a different project I had that has the input JSON, and essentially it just defines the values that you're passing in to that particular circuit. And so we're saying player 1 plays 2, and player 1 plays 5, and player 1 plays 2. And so now that we have the input created and we have the rest of the files here, we could come into this folder now, do quick, let's just confirm we have everything there. And we could now generate the witness. And as you can see, the witness is now generated there. That allows us to then kick off the Powers of Tau ceremony, which is a ceremony that we use to kind of reduce, which is the main criticism of Snarks in general sometimes when you're considering the fact that you have to have a trusted setup, and this is like a multi-party ceremony that we kind of use to be able to generate the keys that will then be used for the subsequent stages of the proof generation. So I'm starting off with the first version of this, and I'm creating the first one, and it creates the first challenge, and there's a contribution hash that is generated as alongside that. And I'm providing the first portion of this. I mean, the first contribution, which I'm just labeling as the first contribution, and I can render a random text and say just my name, tonyolendo, and that's generated there. And if we continue then further, we could do the phase 2 as well. And yeah, sorry, we're back. That typically takes a bit of time for us to be able to get there. And from there, we generate like the key, which essentially we're retrieving the, I mean, I could just drop this in here. But yeah, you have the rank one constraint file that you have to reference. Yeah, so once you reference that, it generates the circuit hash, and you have the key that is available for you there. You could do the second contribution now. No, we could do a different name now here. And we have that portion there, and then we could export a verification key. Now we have a verification key that exists here that we could use based on Route 16 and the curve, the elliptical. Yeah. And yeah, once we have that particular piece, we could generate the proof. And we should have everything that we need inside of this specific folder. And that's it. We have the key. We have everything that we would have required for that. And with that, we could generate our Solidity file, which we'll find inside of the same folder now. And if I come inside of this particular folder, I could see a verifier.so, and the specific file might seem very, very complicated, but essentially when you drop this in when you drop this verifier contract in, well, if you choose to deploy it, you could deploy it anywhere on any EVM, and all you significantly be calling is this verify function on 9250. And for that, we have a handy function that allows you to even generate the call data. And once you have the call data there, it gives you stuff that you could push, well, you could push into this particular file and use that to generate the call data for the verifier.so. And you could drop this in your favorite IDE or even like Remix, which should have everything that you need here. So even if you come to Remix, you could create a new contract here. Call it verify. There you are. Yeah, it might have some compilation errors just based on the version of Solidity and what you have here, and you have to go through that carefully to ensure that you could upgrade. But that essentially enables you to be able to run this application, deploy it anywhere, and that's your basic intro to Circom, from generating and basically defining a circuit all the way through to deploying it on an EVM of your choice, preferably Polygon ZKVM. And that's it for today. So thank you very much, and I hope this was useful. I'll be sharing links to the folders that have the content below, to my previous articles as well, and further information that I just glossed over just because of time. Yeah. Well, thank you, and I hope this was useful.